networks, perhaps deep ones with several layers, and for which we have training using backpropagation, which we mentioned previously. And the idea of backpropagation using the quadratic cost function was that when the weights were badly wrong, the learning was slow. And in order to avoid this situation, a new cost function has been introduced, this one, cross entropy. And in the last slide, last week, we demonstrated that if we want such a thing, or such a thing, then if we integrate, then we get a system of equation which gives the gradient of the cost function with respect to the weights, which are this one. And you see here, you don't see any more of the derivative of the sigmoid function. So this derivative with this gradient depends only on the difference between what we get and what we want, multiplied by the input pattern. Similarly, this cost function derivated with respect to with the gradient with respect to b. So if we wanted not to have derivatives of the sigmoid function, then it is not a miracle that we got this cost function, which is the cross entropy. A comment on this cross entropy cost function is that this is a standard way of interpreting the cross entropy that comes from the field of information theory. So this cross entropy is a kind of measure of surprise intuitively. So if a neuron is trying to compute the function y as a function of x, remember that y is the desired and x is the input pattern. But instead of doing this, it is able to compute the function which gives a to x to a of x, being the activation. So if the activation a, so that means the output, in the output neurons, the probability is, we can think of this a as a probability which that is 1 and 1 minus a, which are the estimated probability that the right value is y is, for instance, 0. The cross entropy measured how surprised we are on average when we learn the true value for y. And we get low surprise if the output is what we expect, and high when the output is unexpected. That's only an intuitive point of view. And now we're speaking about slowdown. Slowdown can occur when output neurons saturate in the networks using the quadratic cost function. Another factor that may inhibit learning is the presence of the xj term in these relations. When xj is small, the input, the derivative with respect to the weights will be small. So we will have a quadratic, we will have a slowdown in learning. This is something which cannot be avoided because xj is given. On the other hand, another possibility of defining the output layer for our neural networks. So remember, we have the output layer and we have the cost. The output layer has activation function which can be sigmoid or something different, as in this case, softmax. So it is similar as with the sigmoid layer, for which we have this notation, but we don't apply the sigmoid function to get the output. Instead, a softmax layer, we apply the softmax function to this ZJL. Remember that L is the last layer. So according to this function, the activation which we compute is this one. So we have information Z related to previous layer, and we compute this thing. And observe that if we sum for all neurons, we get 1. And as a simple example, for softmax function is this one. When ZL are the values here, the softmax is this one. When ZL are different, the softmax will be different as well. But the interesting thing and nice one is that this softmax output can be considered as a probability. Summation of all values gives 1. So this is a probability distribution. In other words, the output from the softmax can be thought, as I said, probability distribution of a finite number of outputs. For instance, in the MNIST classification, we interpret AJL as the network estimating probability that the correct digit classification is J. So if we have a 7, for instance, and we get 0.8, that means that this is the probability with which this image was a 7. The higher, the better. By contrast, the output layer was if the output layer was a sigmoid, then we certainly couldn't assume that the activation form a probability. Remember that the sigmoid was something like this. I sketch on the screen. And if we consider all outputs from all output neurons, there is no proof and no reason that these values sum up to 1. So the difference related to sigmoid layer is that in this last case, we cannot consider the output as being a probability. So of course, in the case of softmax, the output sums to 1 from the definition. So this is a natural way to ensure that the output activations form a probability distribution. So we can think of softmax as a way of rescaling ZJL and then squishing them together to form a probability distribution. So the softmax was related to the nonlinearity of the output layer. And now, regarding to this softmax nonlinearity, we introduce another cost function, which is log likelihood. The cost function is related to the fact that the learning slowdown problem, we already have seen these things using softmax layers of neuron, but we should see how we can address the learning slowdown problem. And if we define the log likelihood cost function and use X to denote the training input to the network and Y to denote the corresponding desired output, then the log likelihood is this one. So remember that the softmax is this one. The cost function is this one. So this is the activation of the output. So for instance, again, if we are training an MNIST image and input an image, for instance, 7, then the log likelihood is this one. This makes intuitive sense if we consider the case when the network is doing a good job, that it is confident that this is a 7. In this case, it will be close to 1, the result, so the cost will be small. In contrast, when the network is doing such a good job, the probability will be smaller and the cost will be larger, so the log likelihood cost behaves as we expect as a cost function to behave. So it is a cost function, and it can be discussed with a relationship to these pairs. So you see softmax associated to log likelihood cost function versus sigmoid associated to cross entropy. So the cross entropy we started with was associated with sigmoid. Now we introduce the softmax as a nonlinearity and log likelihood as a cost function. And it can be seen, it can be obtained that dc to db is this one and dc to d wjkl is this one. So we observe that in this case we don't have the x's xjl. Here we have akl minus 1. So again, the gradient is related to the difference between the output desired and real, here as well with respect to the weights. And here we have a multiplicity factor, which is akl minus 1, which is represented by the output of the previous layer. So they are similar with those obtained with cross entropy. And it is useful to think of a softmax output layer with log likelihood cost as being quite similar to the sigmoid output layer with cross entropy. So since we see this similarity, we use a sigmoid and cross. So we ask ourselves, what is better? So the result, well, the answer is that in many situations, both approaches works well. So remember again, we have sigmoid. We had sigmoids from the beginning. Sigmoids were in the first part of this lecture associated to quadratic, and we saw that in this association we have slowed down. So the same sigmoid as output layer are associated with cost function, which is cross entropy. The alternative is to define another nonlinearity, which is softmax, and which has the advantage of being interpreted as a probability, and the cost function is log likelihood. And so this opportunities and options can be replaced one with the other one. It seems that softmax plus log likelihood is worth using whenever you want to interpret the output as probabilities. But this is not always a concern, because in fact, even though the output of the output layer will not sum to 1, then we will have various values which appear because of the input pattern. So not always is important that the outputs sum up to 1. Softmax is the name which appears because if we consider C tends to infinity in this expression, then we have, if we consider C equal 1, we have this the softmax equation. And if we speak about backpropagation with softmax and log likelihood, then you remember that, so I'm speaking now about training to do training, I remind you that we spoke about backpropagation. Regarding this backpropagation, the first equation in backpropagation was this one and this one, and for using this expression, we can apply backpropagation to a network using softmax output layer and log likelihood costs. Now we are speaking a little about overfitting and regularization. So neural networks have a large number of free parameters. Even if such a model agrees well with available data, it doesn't make that it is a good model. It may just mean there is enough freedom in the model without capturing any genuine insight into the underlying phenomenon. The problem is that a model may work well for existing data, but will fail to generalize to new situation. This is the true test to make prediction in situation that it has not been exposed before. So we give an example from the MNIST database. We have 30 hidden neurons. Remember that the database has a lot of 50,000 digits, images, and for 30 hidden neurons, the network will need 24,000 parameters. A lot, and in the same time not too many if we think of other situation when deep neural networks sometimes contain millions or even billions of parameters. And of course, the problem is that if we can trust these results, and that's what we are discussing now. In order to make an image about overfitting, we will consider only 1,000 images, 30 hidden neurons with 23,860 parameters. But the network will be trained not with the 50,000 minutes training images, but only with 1,000 training images. So the number of images we are training the network is much smaller. So the train will be similarly using the cross entropy cost function with learning rate. Remember, eta has been chosen 0.5 and the mini batch size of 10. Remember that an interesting thing is that using mini batches, that means that you do the same computation for 10 images, and finally you compute or you update the weights. So you don't update the weights for each image, but you compute and you update the weights with the average value corresponding to the mini batch of size 10. And then you take another mini batch of size 10 and so on. And remember that when all images have been considered, then we say that we made an epoch. And the training was done for 400 epochs, a rather large number, because we are not using many training examples. As we will see, a fundamental requirement when we use neural network is to have as many training examples as possible. And in this case, we discuss the result we can plot the way the cost changes as the network learns. So we have here, for the situation we discussed, and for 40 epochs, 400 epochs, what the cost function is doing. Remember again that we are using here a cross entropy cost function. So this is what happens when we train with the cost function. And now appears the surprise. We discuss how the classification accuracy on the test data changes over time. So you have here 400 epochs, and we see that you remember that we have train data and test data. Test data are necessary to see if the network has the capacity of generalizing. And we see here that the accuracy of classification of the test data has a limit which cannot be surpassed anymore. That's the thing which is somehow strange, because if we looked only here, we would have been very happy. We said, well, the cost function is decreasing, so the network is learning and learning, and it is better and better. On the other hand, the true proof that the learning has been, or the network is well trained, is not on the train data, but on the test data. And we see here that in the first epochs, the train data accuracy is increasing, but then stopped, even though the cost is decreasing. So observe here that the epoch when the test data started to stop increasing is something 280. While at 280, we still can decrease the cost function. That's overfitting. So constant with this earlier graph, where the cost associated to the training continues to smoothly drop. If we just look at the cost, it appears that our only at the cost is getting better. But the test accuracy shows that this is an illusion. And we discussed this after 280, no longer generalized to the test data. And it is not useful learning. So we say that we got overfitting or overtraining beyond epoch 280. So we should discuss the relationship between cost versus classification accuracy. So looking at the cost on the training data, as opposed to the classification accuracy on the test data, what is wrong, we should ask ourselves. So what would happen if we compare the cost on the training data with the cost on the test data? So remember, we have accuracy and costs, and we can compute cost for training data and for test data. So now we are speaking about the cost of the test data. We saw this as the test classification accuracy, but now we want to see what is the cost, what does the cost of the test data. So it is in this way we are comparing similar measures. So it is a problem. What should we compare, the classification accuracy on both, or to compare the costs? In fact, essentially, the same phenomenon shows up no matter how we do the comparison. For example, if we look at the cost data, the cost data of the test data, the cost of the test data, we get this. And this is interesting because it represents for the test data what happens with the cost of this test data with respect to the epoch. And you see for the test data, which are independent of the training data, we see that the cost is decreasing. And now, surprise, after epoch or around epoch 15, the costs start to get worse, even though the cost on the training data is continuing to get better. So the cost of the training data, that graph which was decreasing, yeah, our model is overfitting. So this is a somehow disappointing behavior, because we would have expected that with the number of epochs, the cost of the test data would decrease monotonically, and this doesn't happen. And this is overfitting for sure. So now appears the puzzle. Which number should we consider? 15, which is here, or 280 as the point which overfitting is coming to dominate learning for the test data. What we really care is improving classification, while the cost of the test data is no more than a proxy for classification accuracy. So it makes most sense to regard epoch 280 as the point beyond which overfitting is dominating learning in our neural network. Another sign of overfitting may be seen in the classification accuracy of the training data. So remember, for the training data, we had a cost function which was decreasing, and the accuracy of this cost data, of the training data, is getting closer and closer to 100%. So here we have no problems. We have the cost function, which is decreasing, and the accuracy for the training data is increasing. The accuracy is increasing up to 100%. So a fundamental major problem is overfitting. This is especially true in modern networks, which often have very large number of parameters, weights, and biases. So to train effectively, we need a way of detecting when overfitting is going on, so we don't overtrain. The obvious way to detect overfitting is to use the approach about keeping track of accuracy of the test data, not the train data. If we see that the accuracy on the test data is no longer improving, then we should stop training. Interesting, this observation. Strictly speaking, this is not necessarily a sign of overfitting. It might be that accuracy on the test data and the training data both stop improving at the same time. So we are not sure that in this way we stop when it is necessary. On the other hand, we should discuss some tricks so that we do not make training with the whole number of images, but with a smaller one, in order to save time. And to do this, validation data have been introduced. This is something which are used for early stopping. So remember that we have train data and test data, but also we have between them validation data. Validation data are data which are used in order to make an image about how the network is going, and if it is going wrong, then we stop and change the hyperparameters, the learning rate, we'll see number of neurons, layers, and so on. So this early stopping, of course, we will monitor what happens with the validation data after the training has been taken, has been completed. And in practice, we won't immediately know when the accuracy has saturated. So we continue training until we are confident that accuracy has saturated. We are speaking about the accuracy of recognizing validation data, not test data. When to stop? It requires some judgment to determine when to stop. Epoch 280 is the place at which accuracy is saturated. It is possible that one's too pessimistic. Neural networks sometimes plateau for a while in training before continuing to improve. This wouldn't be a surprise. If more learning would have occurred even after epoch 400, although the magnitude of any further improvement would likely be small. So, is it possible to adopt a less aggressive strategy for early stopping? So early stopping again is when to stop training in order not to have overtraining. So we are speaking again about the hyperparameters, and we discuss why to use validation data to prevent overfitting rather than test data. So we could have used test data as well, but in fact, this is part of a more general strategy, which is to use the validation data to evaluate different trial choices of hyperparameters, number of epoch, learning rate, best network architecture, as I already said. So we use such evaluation to set good values for the hyperparameters. Validation data help finding good hyperparameters. So we can think of the validation data as a type of training data that helps us learn good hyperparameter. This approach to finding good hyperparameter is sometimes known as the holdout method, since the validation data is kept apart or held out from the training data. So, of course, we will not validate with the same images we use to train. So, if we are coming back to the mini-train and test without validation data, we'll keep all other parameters the same. Remember, we used in the previous example 30 hidden neurons, learning rate 0.5, mini batch size 10, and train using all 50,000 images. So this time, not 1,000 images have been considered, but 50,000 images for 30 epochs. And we will have immediately a graph showing the results for the classification accuracy on both the training and test data. So there were no validation data used here. We have used the test data rather than validation to make the result more directly comparable with the earlier graph. So again, the hyperparameters 30 hidden neurons, learning rate 0.5, mini batch 10, and training number of 30,000, and the test 10,000 as we spoke previously. And you look at this graph. With yellow, you have the accuracy of training data for 30 epochs. So we have 30 epochs, and the training data is ready to reach 98%. On the other hand, you see the accuracy of the test data, which is blue, which is this one. So you observe that the test data accuracy is increasing much slower than the test data, the training data. So you see here a difference between now it's 97, now it's 95, around here 95, and here we have 90, 97, 98. So keep in mind this image, and let's go on and observe that for 50,000 training data, better than 1,000 training, increase size of training data. So we have better results. The accuracy remain closer, much closer when using 1,000 than when we're using 1,000 examples. So again, the accuracy when we used 50,000 is closer one to the other. So in particular, the best classification accuracy of 97.87 on the training data is only 2.53% higher than 2.53, higher than that of 95.33 on the test data. We are speaking about this difference. Yeah. That's compared with 17.73% gap, which has been obtained for 1,000 samples. We got overfitting, but it has been greatly reduced. Our network is generalizing much better from the training data to the test data. In general, one of the best ways of reducing overfitting is to increase the size of the training data, as I already said. With enough training data, it is difficult for even a very large network to overfit. Unfortunately, training data can be expensive or difficult to acquire, so this is not always a practical option. So we are speaking, in fact, about databases. So it is simple to say that when we want more training data, but the problem is how do we obtain them and how good they are. Now we are speaking a little about regularization. Overfitting can be avoided when we use a large number of training data. If there are other ways to reduce the extent to which overfits occur, a possible approach is to reduce the size of our network, the size of the neural network. So, on the other hand, intuitively, large networks have the potential to be more powerful than smaller networks. So, it is not the best solution to reduce the size of the network. And the trick is what is called L2 regularization. So we have a fixed network and fixed training data. The technique is regularization. One of the most commonly used is a technique known as weight decay or L2 regularization. The idea is to add an extra term to the cost function, a term called the regularization term. Here is the regularization cross entropy. So remember, the cross entropy we spoke about was this one. We have 1 over n being the number in the mini batch, examples in the mini batch. But we have an extra term here. This extra term is the sum of squared values of the weights weighted with lambda, which is the regularization parameter. So we have another parameter, which is a hyperparameter, in fact, this lambda, which should be put here, and nobody will tell us what is its value. So this is another reason to use validation test sets in order to get rather quickly an image about how lambda should be. So lambda is the regularization parameter. So here you see the usual expression for cross entropy, but we have added a second term scaled by lambda over 2n. And then is the size of our training set, or on the mini batches if we use various lambda for various batches. Other options. We can affect with this regularization parameter not necessarily only the cross entropy function, cost function, but also the quadratic. So if we use this quadratic function, then the cost function is the previous one plus this term, where C0 is the original unregularized cost function. So the intuition regarding this regularization is that the effect of regularization is to make it so the network prefers to learn small weights, all other things being equal. Large weights will only be allowed if they considerably improve the first part of the cost function. Put another way, regularization can be viewed as a way of compromising between finding small weights and minimizing the original cost function. The relative importance of the two elements of the compromise depends on the value of lambda. When lambda is small, we prefer to minimize the original cost function, but when lambda is large, we prefer to small weights. So looking here again, or here, we see that if lambda is small, then we can allow large weights. If lambda is large, then this term will penalize substantially the cost function. Remember, from here we have a positive number, from here we have a positive number. We want all this sum to be as small as possible, and this is the compromise between how large we let the weights to increase or how small we need them. An example. So we will give an example showing how regularization reduces overfitting. So we need first, would you like to make a break?
It will be good.
Okay, so let's stop a little and then we will consider going on. Okay, can we continue?
Yes, of course.
So we are speaking now about this idea of regularization, which means taking into consideration another term in the cost function, no matter if it is cross entropy or quadratic, like here. So the main idea is to try to reduce through this technique, to reduce overfitting. And before doing this, we should discuss how to apply our stochastic gradient descent learning algorithm. So in a regularized neural network. In particular, we need to know how to compute the partial derivative for all weights and biases in the network. And if we take the partial derivatives, we observe that previously we had dC0 to dW here, but we also should derivate this term as well. And we get this. So the gradient of the new cost function with respect to W and B is this one. So you observe that B is not affected, but the W's are affected with this term. So the gradient is greater if W are larger and if lambda is large. So it is simple to adapt the backpropagation techniques. So in order to compute the gradient, we use the backpropagation as usual, but we add the term this one. So with this one, the backpropagation will work as usual. The partial derivative with biases are unchanged, so this is a good news. And the learning rule will be, remember that the learning rule should be the weights are updated according to the gradient of the new cost function. And the new cost function is this one. And it is something which is similar to the usual gradient descent learning, remember. But we have to first rescale the weights W by a factor 1 minus eta lambda over n, the weight decay. At first glance, it looks as though this means the weights are being driven unstoppable towards zero. But the other term may lead to weights that increase, so doing causes a decrease in the unregularized cost function. The translation of what I said is that if we had only these terms, then the weights will go to zero, because each time you multiply the weight with something which is less than unity. But we should take into consideration this term as well, which can be this one. This term can counteract the decrease of W. So this is a kind of trade-off for computing the new weights. So if we use mini batches of value M training example, the regularized learning rule will be this one. When we made this average of the gradient of the cost function for a given X for all elements of the mini batch, and we also have the regularization coefficient, which is here. So again, we have not only the learning rate, eta, but also the regularization. You see, this is the rule which is used in the backpropagation to update the weights. It is exactly the same as for gradient, stochastic gradient descent, except for the presence of this term, which contains lambda. For biases, we have something which does not depend on lambda. And now the good news. The effect of regularization of classification. We use, again, a network with 30 hidden neurons, a mini batch of 10, learning rate 0.5, and cross entropy function. Cross entropy function as a cost function, not quadratic. However, this time has been used the regularization parameter lambda equals 0.1. And remember that the cost is this one. And the accuracy of the test data is this one. And if we go to the next slide, we can make a difference. So cost on training data with regularization goes like this, and the accuracy on the test data is increasing up what did not happen in the previous situation. So compare the upper row with the lower row and see what is the benefic effect of regularization. So we are speaking about better generalization. The use of regularization has suppressed overfitting, and the accuracy is considerably higher, with a peak of 87.1, compared with 82% obtained with unregularized case. So we could almost certainly get better result by continuing to train past 100 epochs. Remember that here we had 400 epochs, but if we continue, it is not unlikely that this increase will continue as well. It is somehow, in a way, a kind of miracle that using a parameter for regularization in the way we spoke about, we got such an improvement in the accuracy of the test data. So it seems that empirically regularization is causing our network to generalize better and considerably reducing the effects of overfitting. It's interesting because this philosophy of it has been found appears in network community very often. So the community counts on empirical results because it is almost impossible to demonstrate for large databases that this is true in a rigorously mathematical manner. So going back to 50,000 images, we have seen that overfitting is much less when we had 50,000 images. And the question is, does regularization help any further, even in this case? So keeping the same parameters, hyperparameters, 30 epochs, learning range 0.5, mini batch 10, we need to modify the regularization parameter. The reason is because the size n of the training data has changed from n to 1 of 1,000 to n equals to 50,000. And this is changing the weight decay factor. Remember that we have here division by n, and if we keep this lambda as previously, we will get a slow influence on lambda because of the value of n. So previously there was a lambda equals to 0.1, and now it has been changed because of this reason to lambda equals 5. And what it has been obtained is a lot of good news. The classification accuracy on the test data is up from 95 when running unregularized to 96.49. So this is one thing. The regularization for the test data increases. Second, the gap between the results of the training and test data is narrower than before. There is still a significant gap, but there will be substantial progress in reducing of overfitting. So good news, which can be represented numerically by this increase from 95.49 to 96.49. Now, another change of a hyperparameter, the number of neurons in the hidden layer. So we use 100 hidden neurons with validation data. So we get with lambda equals 5.0, the final result is a classification accuracy 97.92. Remember, here we have 96.49. So what has been done was to change the number of the hidden neurons from 30 to 100. This is a big jump from the 30 hidden neuron case. Tuning just a little more to run for 60 epochs and eta equals 0.1 and lambda equals 5, we surpassed the 98% barrier, achieving 98.0.5. Tuning a little more and running for 60 epochs. Not bad for, he says, only 152 lines of codes. An observation is that the unregularized runs will occasionally get stuck, apparently caught in local minimum of the cost function. You remember the cost function can have local minimum, and it seems that if you run differently the same network, we can obtain quite different results. What changes from one run to the other one is the set of weights which has been used. You remember that when we start to train a network, we have to choose some weights in a random way, and it depends on what are the first weights which has been chosen randomly. One time we can get something, another time with other randomly chosen weights, we can get something more or less different. On the other hand, this happens no more when we have regularized runs, and the results are more easily replicable. Exploration. If the cost function is unregularized, then the length of the weight vector is likely to grow, all other things being equal. This can cause the weight vector to get stuck pointing in more or less the same direction. So we have big values or W, since changes to gradient descent only make tiny changes to the direction in which the length is long. So if we have large weights, it is unlikely that these large weights will change and become smaller. This is making it hard for our learning algorithm to properly explore the weight space and harder to find good minima of the cost function. And the solution is to use regularization. And the example is here, how regularization helps reduce overfitting. It is a well-known example often given. If you have this data, so we would like to have a model for this data set as a training set. A possibility is to model with a polynomial. So instead of using neural networks, we use a polynomial. But remember that a neural network, what is doing, it is building, synthesizing a function. So for polynomials, things are easier and more intuitive to be understood. So we will go to neural networks soon. Now there are 10 points of the graph, so it is possible to fit exactly with this polynomial, which will mean that we have such a thing. And so this is an exact fit. Well, at a first glance, we should be wonderful. We are lucky. We are happy. We succeeded to fit all the training data into this model. And the problem is we can get a good fit using the linear model, this one. And the problem is which is better. Interestingly, even though heuristically it is not possible to explain why, the second one is better. It is not a priori possible to say which is correct. Maybe there is a third possibility, because always when we are working with neural network, we have some unknown. The test data, it is not used during training. So the difference between the two models is, for the data, is simple. But if we want to predict the value of y corresponding to some large value of x, if we try to do this, there will be a dramatic difference between the prediction of the two models, as the ninth order polynomial comes to be dominated by the x at the ninth power term, while the linear model remains linear. So here, if we want to predict values like this, it is very likely that they will be along this line. While in this situation, if we want to predict pairs here, x and y, then you see that the model will give, if the point is here, the model will give completely wrong values and prediction. So we suspect that the model must be expressing some underlying truth. That's very nicely expressed, underlying truth about the phenomena. In this case, at hand, the model plus noise seems to be much simpler than this one. It would be surprising if that simplicity had occurred by chance. So we would suspect that this equation expresses some underlying truth. The ninth order model is just really learning the effect of local noise. If we want to change a little the points, then the ninth order model will feel this, but will be sensitive to local noise. And while the ninth order model works perfectly for this particular point, the model will fail to generalize to other data points, and the noisy linear model will have greater predictive power. This is a kind of compromise, and well, let you think about a kind of contradiction between the appearance that a better fit is good and what happens that because of the underlying truth, we have possibility of being more precise for the test data. So small weights are less sensitive to local noise because they work together. If we have small weights, as it will tend to happen a regularized network. Remember that the lambda is weighting the summation of weights. So lambda will impose small weights. The smallness of the weights means that the behavior of the network won't change too much if we change a few random inputs. It is difficult for a regularized network to learn this effect of local noise in the data. So instead, a regularized network learns to respond to types of evidence which are seen often across the training set. So it is better to have smaller weights which are less sensitive to local noise. Large weights can lead to significant changes. So if we change a large weight, then the function will change substantially, and large weight may change its behavior quite a bit in response to small changes in the input. So the unregularized network can use large weights to learn a complex model that carries a lot of information about the noise in the training data. So regularized networks are constrained to build relatively simple models based on patterns seen often in the training data, and are resistant to learning peculiarities of the noise in the training data. The hope is that this will force our network to do real learning about the phenomena at hand and to generalize better from what they learn. The morals. It can be a subtle business deciding which of the two explanations is truly simpler. So we are speaking about the fact that here examples count and intuition comes from experience. Second, even if we can make such a judgment, simplicity is a guide that may be used with a great caution. Simplicity must be used with great caution. The true test of a model is not simplicity, but rather how well it does in predicting new phenomena in new regimes of behavior. A still hot topic. It's an empirical fact that regularized neural networks usually generalize better than unregularized networks, but no one has yet developed an entirely convincing theoretical explanation for why regularization helps network generalize. Researchers continue to write papers where they try different approaches to regularization, compare them to see which works better, and attempt to understand why different approaches work better or worse. And so you can view regularization as something of a kludge or improvisation. It often helps, but we don't have an entirely satisfactory, systematic understanding of what's going on, merely incomplete heuristic and rules of thumb. Contrast to humans. This is particularly annoying, because in everyday life we humans generalize phenomenally well. Show just a few images of an elephant, the child, and she will quickly learn to recognize other elephants. So we have a system, the human brain, with a huge number of free parameters, the connection between the neurons, and after being shown just one or a few training images, that system learns to generalize to other images. Our brains are, in some sense, regularizing amazingly well. And how do we do this? We don't know. Perhaps in years to come, we'll develop more powerful techniques for regularization in the artificial neural network that will ultimately enable neural network to generalize well, even from small data set. I doubt this sentence, because, well, it is for sure that the smaller the data set, the more difficult to train the network. Also, it's interesting that biases are not regularized. L2 regularization doesn't constrain the biases. Empirically, doing this often doesn't change the result very much. So it is possible to try to regularize biases, but it seems that this has been found that there is not much to gain from this. So it's merely convention whether to regularize the biases or not. It is worth noting that having a large bias doesn't make a neuron sensitive to its input in the same ways as having large bias. So we don't need to worry about large biases, enabling our network to learn from noise in our training data. At the same time, allowing large biases gives our network more flexibilities, large biases in behavior. In particular, large biases make it easier to neuron to saturate, which is sometimes is desirable. Other techniques for regularization. There are many. One of them, L1, regularization dropout and artificially increasing the training set. So another type of regularization is the L1 regularization. It doesn't use the square of the W's. The other one is dropout, which means that we keep some neurons and we do not consider some others in the hidden layers. And a very nice, interesting thing, artificially increasing the training set size. We will do some very short covering of these ideas. The L1 regularization. We modify the unregularized cost function by adding the sum of the absolute values of the weights. So the difference is this one. Previously we had W square. Now we have module of the absolute value of W's, summation and divided by the number of examples. So if we take the partial derivative, we have this gradient of the cost function, which is the gradient of the previous cost function, which has not been affected by regularization, plus this term. So the resulted updated rule for an L1 regularized network is this one, or compared to L2 is this one. So we observe that here the previous situation was this one, and now we have a constant thing here. So the constant thing is much broader than what we had with L2. In both expressions, the effect of regularization is to shrink the weights and penalize large weight, but the way the weights shrink is different. In L1, the weights shrink by a constant amount, as I said previously, towards zero. In L2, the weight shrinks by an amount which is proportional to W. And so, when a particular weight has a large magnitude, L1 regularization shrinks the weight much less than L2. If W is large, the sign is plus minus 1. By contrast, when W is small, L1 shrinks the weights much more than L2 because we have a W small, but again, plus minus 1 is this time larger than the W's. So that's L1 regularization tend to concentrate the weights of the network in a relatively small number of high importance connections, while the other weights are driven towards zero. This is for the L1 regularization. Dropout. The main idea is to modify the network. So far, we modified hyperparameters with related to the regularization parameter lambda or the speed of learning rate. And the idea is to delete half of hidden neurons. Suppose we have a training input and the corresponding desired output Y. Ordinarily, we train by forward propagating X through the network and then back propagating to determine the contribution to the gradient. With dropout, we start by randomly deleting and temporarily deleting half of the hidden neurons. So half of this neurons are deleted, while leaving the input and output neurons untouched, input and output. So this happens only in the hidden layer. After doing this, we'll end up with a network along the following lines. Note that the dropout that have been temporarily deleted are still ghosted in this situation. So half of the neuron here have been deleted. And then we repeat, we forward propagate the input X through the modified network and then back propagate the result also through the modified network. After doing this over a mini batch of example, we update the appropriate weights, and biases, and then repeat the process, first restoring the dropout neurons, then choosing a new random subset of hidden neuron to delete, estimating the gradient for a different mini batch, and updating the weights and batches and biases in the network. So we are dropping out some neurons, we are using backpropagation, and then we affect differently the hidden layer and choose other neurons to be dropped out and other to remain, half deleted. But in this situation, we repeat, and finally the network will learn a set of weights and biases. Of course, these weights and biases will have to be learned under condition in which half the hidden neurons were dropped out. When we actually run the full network, that means that twice as many hidden neurons will be active. To compensate for this, we have the weights outgoing from the hidden neurons. So finally, the neurons will have various values for the dropped out architecture. And at the end, all weights are put together and all cells are used. All neurons are used in the hidden layer. So the weights outgoing from the hidden neurons will be halved because there will be twice as many. Intuition. The reason is that the different networks may overfit in different ways, and averaging may help eliminate that kind of overfitting. So different networks may overfit in different ways. So this is why dropping out at each step another number of neurons or other neurons, the number is half of the neurons on the hidden layer. Heuristically, it is like we are training different neural networks. And the hope is that the dropout procedure is like averaging the effect of a very large number of different networks. That's the intuition behind dropout. The different networks will overfit in different ways. So hopefully the net effect of dropout will be to reduce overfitting, which happens. The true measure of dropout is that it has been very successfully improving the performance of neural network. It is presented here, a paper, Geoffrey Hinton, Srivastava, and Krzyzewski, plus Skever and Salak Tudiov from 10 years ago, who succeeded to get very nice results using the MNIST database for digital classification with an ordinary feed-forward network similar to those which have been considered. The paper noted that the best results anyone has achieved up to that point using such an architecture was 98.4% classification. They improved it to 98.7 using a combination of dropout and modified form of L2 regularization. Dropout is especially useful in training large, deep network where overfitting is often acute. The philosophy, what you have heard and seen on this slide, is that people make experiments. So there is not a precise theory that will say, well, you should make so many runs and using how many dropouts you will use and so on. So those guys succeeded to get such results by experiments. A related heuristic explanation from dropout is given in this paper by Krzyzewski, Skewer, and Hinton. Regarding robustness, if we think of our network as a model which is making prediction, then we can think of dropout as a way of making sure that the model is robust to the loss of any individual piece of evidence. This is something similar to L1, L2 regularization, which tend to reduce weights and thus make the network more robust to losing any individual connection. So it's interesting that the dropout can be seen as a robustness improvement. This is a very nice observation and solution. Artificially expanding the training data. If we train using mini batches of 10, a learning rate eta equals 0.5, regularization lambda equals 5, and cross entropy function, and it has been trained for 30 epochs. When the full training set is used and scale up the number of epochs proportionally when smaller training sets are used, to ensure the weight decay factor remains the same, we use the regularization parameter lambda, this one, when the full training set is used, and scale down lambda proportionally to smaller training used. And what has been got like this is accuracy on the validation data with the training set. You see, this graph has been for the first time put in the slides because we are speaking about the increase of accuracy with the number of elements in the training set. We already said that a fundamental thing in training neural network is the number of elements in the training set. And you see here an image of what happens if we have few elements. If we have few elements, it is not possible to get good results on the validation set. So here we have the training set, and the number of elements is up to 50,000. And now we would ask ourselves if we could continue, if we had instead of 50,000, we have 60,000 or 70,000, but the database is finite, so we don't have larger databases. So we would like to get more data from a given data set without doing other signal or pattern acquisition. So what would it be if instead of 50,000 we would have 1 million? It is expected that we likely get considerably better performance, even from this very small network. And the idea is represented here. Having more data is a great idea, but it has to be expensive, so you should use other people to write or to draw digits and so on. The other idea is, suppose, for example, that we take a mini training image of a 5, and rotate it by a small amount. So we have this 5 and we rotate it and we get this. This is an artificial way of producing a new element. So compare this solution, which is rather elegant, to the solution when we should look for other people to produce other drawings. So expanding the trained data set means that we can expand by making many small rotation of all MNIST training images and then using the expanding training to improve our networks. The idea was used. There are some results which has been published here. One of the neural network architecture they consider was along similar line to what we have been using, a fit-for network with 800 hidden neurons using cross entropy as cost function. So running with standard MNIST training data, they achieved a classification of 98.4 with the standard MNIST. 98.4% of their test set. But they expanded the training data, not just rotation, but also translating and skewing the images. By training on the expanded data, they had increased their network up to 98.9. They also experiment what they call elastic distortion, a special type of image distortion intended to emulate the random oscillation found in hand muscles. So we are speaking about various techniques to expand the database. By using this elastic distortion, about which I'm not able to tell much more than you have heard here, to expand the data, they achieved an even higher accuracy of 99.3. Effectively, they were broadening the experience of their network by exposing it to the sort of variation that are found in real handwriting. Another idea is adding noise or filtering. Many learning tests can be considered not just hand reading recognition. In general, principle is to expand the training data by applying operations that reflect real world variation, and in this way to improve and to expand the database with, let's call more or less artificial new example, but not completely artificial. If you are building neural network to do speech recognition, we can, as humans, recognize speech even in the presence of distortion, like background noise. We can expand data adding background noise if we are speaking about speech recognition. We can also recognize speech if it's sped up or slowed down. These techniques are not always used. Instead of expanding the trained data by adding noise, it may be more efficient to clean up the input by first applying a noise-reducing filter. The idea here is that sometimes instead of inventing new input patterns, we can filter the existing input pattern and use them as training data. This is a comparison between neural network results with blue and support vector machines with yellow. And it has been seen, it is seen that neural network accuracy does better. Sometimes support vector machines are doing better, but if you compare two techniques, it is important to know how many images have been used in order to make the training. So, in other words, more training data can sometimes compensate for differences in the machine learning algorithm used. If we use two algorithms, sometimes even more interesting can occur. We are trying to solve a problem using two machine learning algorithms, algorithm A and B. And sometimes it happens that algorithm A will outperform algorithm B with one set of training data, while B will outperform with A with a different set training data. That's very nice to think about it. So instead of comparing the algorithm, we should consider the correct response to the question, is algorithm better A better than algorithm B? The real response is a question. What training data set are you using? So that's interesting because even when we want to compare results, we should be careful. So the message to take away is that what we want is both better algorithm and better training. It's fine to look for better algorithms, but make sure that you are not focusing on better algorithm to the exclusion of easy wins, getting more or better training data, including using this data extension, which I spoke about. Well, I hope you are tired enough of my speech. So let us stop here, and we will meet last time this year, next Thursday.
Okay, thank you.
All the best.
Thank you. Bye.
Have a nice day.